All right, so we did this problem in class, and I'm going to do it a slightly different way. I'm going to do it to scale. So I think I mentioned that you could do these problems by scaling using a protractor and a ruler. So what I'm looking at here is we've got the 600 Newton force at a 30-degree angle from the horizontal and the 400 Newton force at a 45-degree angle from either the vertical or the negative horizontal. And you can see when we use the parallelogram rule, we basically drew the 600 Newton vector and we connected the 400 Newton. Essentially, this is the tip to tail method as well as parallelogram method. So the parallelogram method is basically taking two vectors and doing tip to tail and then drawing the diagonal. So this is that direction. So what I'm going to do is I'm going to draw these two vectors to scale and measure the angles. Well, I'm going to set the angles and then I'm going to measure the angles. And we're going to do that on this new piece of paper here. So let's see, I've got a line here. And what I'm going to do for my scaling is I'm going to say, let's see, I think I'll say 2 centimeters is 100 newtons, right? So we have a 600 Newton force and a 400 Newton force. And so the 400 Newton force, if 100 newtons is 2 centimeters, 400 newtons is 8 centimeters, right? And similarly, the 600 Newton force is going to be a 12 centimeter line. Let's hope I left enough room there. Let's see, I'll pause this for a minute. Yeah, I'm pretty sure I left enough room. All right, so we're going to start down here. First thing I'm going to do is I'm going to draw the 600 Newton force at an angle of 30 degrees. So I'm going to draw a 12 centimeter line at a 30-degree angle from the horizontal. And this is my horizontal, so I'm going to put my protractor here. And then let me just line this up. All right, so we want 30 degrees from the horizontal, 10, 20, 30. Do that. Draw this in. There's no connection point there. We want 10, 12. All right, so we double check the angle here. Yeah, it's 30 degrees. All right, so let me label this 30 degrees. All right, so that's the 600 Newton force. So let's write that here. And one thing I'm going to do here is I'm going to draw a, let's see, I'm going to do this. I think I'll do this upside down like this. So I can draw a horizontal line here, approximate. I'm just going to draw myself a horizontal line so I have another reference line to draw the 400 Newton force off of. You grab a pencil here. Be a nice light line. All right, so now I'm going to draw my 400 Newton force at an angle of 45 degrees from the horizontal, but I'm connecting the tail of the 400 Newton force to the tip of the 600 Newton force. Let's get this all lined up here. And what did I say, 45 degrees, 20, 30, 45. Approximately there. And a 400 Newton force is 8 centimeters. So let's draw 8 centimeters in here. Well, this is going to be, I've got to move the camera so I can look straight down on this when I draw the line. I'm going to go through that point, that point. That's approximately lined up. Now you can always expect some error doing it this way. I'm going to say 8 centimeters. That's right there. And so this is a 45-degree angle. We should probably should have measured twice, drawn once. Like the old adage, yeah, it's 45 degrees. Measure twice, cut once, 45 degrees. And this is our 400 Newton force. All right, so now all I have to do is I have to draw my resultant in here. Let's see. So I'm going to draw my resultant from the start here, right, to the finish there. Oops, this ink is smearing. Do that. And I'm going to measure this. This is our resultant. So I'm going to measure the length of this thing. We just turn this sideways so we can easily do this. Starting with 0. And it's kind of hard to see, but it looks somewhere between 12.5 and 12.6, call it 12.55. So this is about 12.55 centimeters. All right. And we need to measure the angle too. So let me take the protractor here, line it up. Over just a tad. Right. All right, so reading this, we've got 10, 20, 30, 40, 50, 60, 5, 6, about 67 and a half or so, maybe. All right, so 67 and a half. Write that angle in. And again, the more time, you measure it the second time, you probably get a slightly different answer, right? Oops. 60. Yeah, that's pretty close. About 67 and a half. All right, so let's rescale this. So I'll do it. I'll do it up here. So we want to know how many newtons this length is, right? So we can use either one of the scales, but let's just take the 100 newtons is 2 centimeters, as x newtons is 12.55 centimeters. Let me get my calculator. All right, so 100 divided by 2 is 50, right, times the 12.55. You get about 627.5 newtons. Right, and our angle 67.5 degrees. So we can write our resultant is about 627 or 628, let's round it, newtons at an angle of about 67.5 degrees. Now this should be pretty close to what we got using the parallelogram rule, and it is close, it's not exact. So with the parallelogram rule, we got 629 newtons at an angle of 67.9. So you see, we're in the right ballpark here. But this method has a lot of potential error, right? Because you're taking and you're scaling this out. So if I'd used a different scale, so maybe 4 centimeters is, or sorry, 1 centimeter is 100 newtons. I could have gone out even longer, right? I would have had oh, sorry, 100. That's backwards. 2 centimeters is 100 newtons. If I had used 4 centimeters, right? Anyway, the longer you make these lines, the more accurate you're going to be. But I just used it. I said, all right, for every 100 newtons, we're going to draw 2 centimeters. And that's where I got these lines from, right? These are to scale. So the 400 newtons, 600 newtons lines are to scale. I drew my angles to scale. And that means this resultant is also to scale. But again, the bigger you draw this, the more accurate you're going to be to more decimals. Assuming obviously you have a ruler that's that's got the resolution to measure everything. So this is the graphical method of solving vector resultant, or sorry, solving for vector resultants. And you can break it down the other way too. You can say, all right, I'm going to take this resultant and break it into an X and Y component, right? And you could get those components, and that should be what you would get similarly with the right triangle method. All right, so hope that's helped.